Alright, good day. So we'll now continue to discuss these topics now under the compression members. Members with slender elements for sections that do not satisfy the width to thickness ratio requirements. So this is the lambda, no? Remember in our previous video, no, in the previous video that I made. So we discussed about those elements now that satisfy, meaning if you remember the table, this table 502.4.1, the limiting values for stiff, for compact and non-compact are this, and this is your lambda width to thickness ratio. So if your lambda will not exceed this limiting value for compact and non-compact, meaning you have to use this provision, no, for unstiffened element and stiffened element, meaning the column, no, is okay. The local stability is not a problem if the lambda or the width to thickness ratio do not exceed or does not exceed these values for compact lambda sub p and the non-compact lambda sub r, no? Sa atong previous example, this one, we check for the local instability. And these values, this b over t and h over tw is already in the table, no, of values in the manual, AASC manual. What if, no, the sections do not satisfy the width to thickness ratio requirements, meaning greater than the lambda sub r and lambda sub p, especially the non-compact. It is permissible to use the cross-section, no, okay lagi hapon siya gamiton, siya does not satisfy the width to thickness ratio requirements, but it is not permitted to carry a load as large as the one that satisfy the requirements. In other words, the strength could be reduced because of local buckling. So you have to compute the nominal strength nga makarry lang siya sa, or the design strength or allowable strength for the LRFD and ASD nga makarry sa those elements or member that do not satisfy the width to thickness ratio. We have here the section that do not satisfy the lambda or the width to thickness ratio requirement. So if the lambda or the width to thickness ratio requirements is greater than this lambda sub r, this is for a non-compact width to thickness ratio. Use the provisions of the NECP 505.7 or AASC E7 and compute the reduction factor Q. That this is not squared but only Q. So Q, wala na siya squared, as provided in SCP 505.7.1 and 2. Then we check for this local stability, no? Kung if this is lambda is less than this lambda sub r, meaning local stability is okay, no problem for local stability. But if this width to thickness ratio is greater than this lambda sub r, then we have to use the reduction factor Q. Then compute for the slenderness ratio KL over R and this F sub E or the Euler effective strength, no? as usual, no, that what we did in our previous discussion. Then compute the FCR and the nominal strength, no. Then this nominal strength for LRFD times the phi or the resistance factor for LRFD, you will get the design strength for ASD divide the factor of safety, no. If this KL over R or the slenderness ratio is less than or equal to 4.71 square root of E over, yes, kanang, if this will if the width thickness ratio is greater than this limiting width to thickness ratio, syempre you have to compute, no, for the reduction factor, then compute for the KL over R. Then if the KL over R is less than or equal to 4.71 square root of E over QFY, now since you already computed your Q, or QFY over E is less than or equal to 2.25, or if FE is greater than or equal to 0.44 QFY, then use this FCR or the critical buckling load equal to Q times 0.658 Q Fy over Fe times Fy as stipulated in NECP equation 505.7-2 or AAS equation E7-2. Q is equal to 1.04 members with compact and non-compact sections as defined in section 502.4 for uniformly compressed elements, or Q is equal to Q sub S times Q sub A for members with slender element section. Remember, the compact is defined, compact and non-compact is defined as compact. For a section to qualify a compact, its flanges must be continuously connected to the webs, and the width to thickness ratio of its compression elements must not exceed the limiting thickness ratio of lambda sub p. Now this is for compact, no. If the width to thickness ratio of one or more compression elements exceed lambda sub p, so lambda sub p for non-compact is lambda sub p exceed lambda sub p so this is your width to thickness ratio actual sigma ay lambda sub r, no, but does not exceed lambda sub r from table 502.4.1. the section is non-compact. And slender element, if the width to thickness ratio of any element exceeds lambda sub r, the section is referred to as slender element section. Slender, no, element. If the lambda is greater than lambda sub r. If the lambda is greater than lambda sub p only, no. Kung for non-compact, kung greater pa gid siya sa non-compact, lambda sub r is for non-compact, meaning slender element na gid siya, no. Meaning the local stability is critical, no, for this element. So it is important to check the local stability of the steel of the element. Okay. Q is equal to 1.04 members with compact and non-compact sections, no. Like the web is compact and the flange is non-compact. So Q is equal to 1.0 as defined in section 502.4 for uniformly compressed elements, or Q is equal to Q sub S times Q sub A for members with slender element sections, no? Those slender element sections. So these slender element sections, somewhat complicated, no? This topic actually is somewhat complicated, lubog siya. But I will try to understand, no? Steps in investigating a section not satisfying a lambda requirement. So kanang, and if or greater than the compact and non-compact, no? With the thickness ratio. If KL over R is greater than 4.71 square root of V over QFY, or QFY, gatong ganina, if KL over R is less than or equal to, no? This time, if KL over R or the slenderness ratio is greater than 4.71 square root of V over QFY, or QFY over FE is greater than 2.25, or FE is less than 0.44 QFY, use this critical buckling load equal to, or strength, no? Critical buckling stress is equal to 0.877 FE as stipulated in NECP equation 505.7-3 or AASC equation E7-3. Then from this critical buckling stress or strength, no, the nominal compressive strength P sub n, no, this is a like usual computation, will end up P sub n is equal to the critical buckling stress or strength times the gross area, no, as stipulated in NECP equation 505.7-1 or AASC equation E7-1. For the reduction factor Q, no, for especially for members with slender element sections, or those with the thickness ratio greater than the non-compact with thickness ratio, the Q is equal to Q sub S times Q sub A. The Q sub S is for unstiffened elements, no? We already discussed the unstiffened elements. And Q sub A is for stiffened elements. Q sub S is equal to 1.0. Atong balik ko na lang. Say we have here the wide flange, no? So the unstiff elements is actually the flanges, no, these flanges. And stiffened elements is basically the wide flange, not all, but naa siya kuan diri stiffeners, no, na siya stiffeners diri, or fillet na siya fillet diha. So meaning this web here, this is stiffened, while the flange is unstiffened elements, no. So actually ang gi reinforce ani or gi stiffened ani is ang web. The Q sub S is equal to 1.0 if the shape has no slender unstiffened elements, and Q sub A is 1.0 if the shape has no slender stiffened elements. So that multiplying this one, Q is equal to 1.0 for members with compact and non-compact sections, no, and no slender. unstiffened element siya pero no slender. I mean, not slender. And stiffened element siya pero not slender. So that your Q is 1 times 1 equal to 1.0 also with compact and non-compact sections. No? Notes. Many of the shapes commonly used as columns are not slender. No? Especially, or the reduction is not needed. Thus, the reduction is not needed. That includes most but not all W shapes. No, kasagara W shapes, not slender. No, so meaning reduction or the coefficient Q is not needed anymore. But a large number of hollow structural shapes or the HSS. Remember the shape HSS, di ba? Murag somewhat square or rectangle hollow or double angles and T's have slender elements. So these members or these shapes need reduction that should be multiplied, no? To calculate Q sub S for slender unstiffened elements, use the NSCP 505.7.1 or AISC section E7.1. To calculate Q sub A for slender stiffened elements, use NSCP section 505.7.2 or AISC section E7.2. Try to visit this section or this, yes, in the NSCP as soon as you watch this video, no, to calculate for the coefficient or the reduction factor Q sub S and Q sub A. We have this Q sub S, which is the slender and stiffened for the slender stiffened element. So try to see the NECP 505.7.1 or AASC section E7.1 for flanges, angles, and plates projecting from rolled columns or other compression members. No, for flanges, angles, and plates. So remember the unstiffened elements for flanges, angles, and plates projecting from rolled columns and other compression members. When B over T, this B over T is can be seen in the table, no, of in the AASC manual. If B over T is less than or equal to 0.56 square root of V over Fy, since this is the limiting value man, di ba? This is the limiting value for compact. No, this is limiting value for compact. If the B over T is less than or equal to 0.56 square root of E over Fy, Q sub S is equal to 1.0. If you try to look at this in ECP section 505.7.1, ano naman to? So, somewhere 507, ito 505. 505.7.1, no? Where are you? 505.7.1. Yes, this one, no? For slender stiffened elements, Q sub S. So, actually, kuha rin siya sa NECP, no? When this B over 2 is greater than or equal to 0.56 square root of V over Fy, but less than 1.03 square root of V over Fy, use this Q sub S equal to 1.415 minus 0.74 V over T square root of Fy over E. But when B sub T, this is for non-compact, meaning this is for slender elements na gid siya, di ba? B over T is greater than or equal to 1.03 square root of E over Fy, use Q sub S equal to 0.69 E over Fy B over T squared. That is for flanges, angles, and plates projecting from rolled columns or other compression members. For flanges, angles, no? Flanges, angles, and plates projecting from built-up I-shaped columns. Built up meaning gi-form siya, no? I believe now you understand built up, meaning this section, bali dili siya built up is gi-combine siya, meaning dili siya like the I shape that is usual I shape nga, meaning gipatong-patong siya, that is built up shape, no? Built up, then gi-paste na siya diha, no? Paste na siya para ma-I shape, then dili na siya, so manang ma-I shape siya. Or other compression members, no? Projecting from built up, no? Meaning built up. When B over T is less than or equal to 0.64 square root of E Kc over Fy, use Q sub S is equal to 1.0. K sub C is equal to 4 over square root of H over TW and shall not be taken less than, so daghan kayo provision, no? Makalibog yun. Yeah, honestly. And shall not be taken less than 0.35 nor greater than 0.76 for calculation purposes. So, kung less than ni siya 0.35, use 0.35, no? If Kc is greater than 0.76, use 0.76. But within this range, 0.35 to 0.76, use the actual value for K sub C. Then substitute, no, in this condition. When this B over T is greater than or equal to 0.64 square root of E modulus of elasticity times K sub C over Fy, but less than or equal to 1.17 square root of EKC over Fy, use this Q sub S equal to 1.415 minus 0.65 times B over T square root of Fy over EKC, no? But when B sub T is greater than, meaning B sub T is greater than, dako na kay siya og B, or the flange, or the height baka na siya, but thickness is grabe ka nipis, no? Is greater than 1.17 square root of, meaning slender na gid siya nga element, no? The local buckling load, local stability is critical, and the local buckling is also like obvious, no? Ingani nga section is greater than or equal to 1.17 square root of E Kc over Fy, use Q sub S reduction factor equal to 0.9 E K sub C over Fy times B over T squared, no? For single angles single, masakitan mapunta ng single, charot. For single angles, like angle bar, no? The Q sub S, no, unstiffened elements, if B sub T is less than or equal to 0.45 square root of E over Fy, use Q sub S equal to 1.0. And if this condition of B over T is greater than 0.45 square root of E over Fy but less than or equal to 0.91 square root of E over Fy, use this use this relation for Q sub S. If B sub T is greater than 0.91 square root of E over Fy, use this relation for Q sub S, where B is the full width of the longest angle leg of the angle bar, no? For single angle, meaning angle bar. Sorry for the drawing, no? Not. So, na siya. The B is the largest full width of the longest, the longest leg. for stems of t's, stems meaning if this is the t, and this is the t, this is t, and this is the d is the full nominal depth of t. When d over t is less than or equal to 0.75 square root of e over fy, use q sub s equal to 1.0. When 0.75 times square root of e over fy, if d over t is greater than 0.75 square root of e over fy but less than or equal to 1.03 square root of e over fy, use this value for q sub s. Formula for q sub s. But when d over t, meaning taas na kay ang d but gamay og t, gamay og thickness. So this is very slender, element. If this is greater than 1.03 square root of e over fy, use this q equal to 0.69 e over fy d t squared. This is for slender and stiffened elements. Now, for slender stiffened elements, q sub a, we have here the provision from NECP section 505.7.2 or AISC section E7.2. The reduction factor q sub a is equal to the area effective over the A. The A is the total gross cross-sectional area of the member. So this is given in the table, in the AISC manual. In A sub effective is equal to summation of the effective areas of the cross-section based on the reduced with BE, millimeter square. So the reduced B sub E can be computed also from the NECP section 505.7.2 or AASC section E7.2. The reduced effective width B sub E is determined as follows. For uniformly compressed slender elements, except flanges of square and rectangular sections of uniform thickness. So, except katong flanges of square, square, except this katubitang HSS, except kani siya nga kuan. So, uniformly slender elements, except this one or HSS, murag HSS ang kuan ani in the pipes. HSS shape ang except flanges of a square and rectangular sections of uniform thickness. So, except na siya. With B over T greater than or equal to 1.49 square root of E over F, use BE or the reduced effective width equal to 1.92 T. This is the thickness. Square root of E over F, small f, times the quantity 1 minus 0.34, daghan kay ko formula, over B over T, square root of B over F, should be less than or equal to B, Of course, because this is a reduced effective width, Where F is taken as FCR, with FCR calculated based on Q is equal to 1.0. I think there is, yes, for the purpose of iteration, substitute the value of F the same with the value of FCR based on the calculated Q is equal to 1.0. Okay, let's have an example now to better understand these provisions or conditions. For number 2 is this one is for uniformly compressed slender elements, except for flanges and square. For number 2 is for flanges of square and rectangular slender element sections, uniform thickness. So, this is for HSS, no? For HSS na ni siya. Shape. HSS shape with, if B over T is greater than or, use this B over T, or if B over T is greater than or equal to 1.40 square root of B over F, B sub E is equal to 1.92 T square root of E, the same, almost the same now formula with the number 1 condition, but the numerical values now is, for number 1 is 0.34 and for number 2 is 0.38. Where F is equal to nominal strength divided by the effective area. User note, in lieu of calculating F, which requires iteration, F may be taken equal to Fy, which is slightly conservative estimate of column capacity. Okay, let's have example now later. For actually loaded circular sections with D, this is the diameter divided by T, greater than 0.11 E over Fy, but less than 0.45 E over Fy, use this Q sub A equal to 0.038 E over Fy times D over T plus 2/3. Actually loaded circular sections, or these are pipes, no? Where D is the outside diameter of round HSS, millimeter, and T, round HSS, no? Millimeter, and T is the wall thickness. Alright, we have here an example.